Question 3 on the 2026 AP Physics 1 exam, the lab question. So here we have students investigating friction using the following procedure. They're going to release a block of unknown mass near the top of a curved ramp. The block will slide down the ramp and then transition to a horizontal surface as shown in figure 1. And there's no friction on the ramp, but there is friction between the block and the horizontal surface. Students are asked to perform an experiment in which a single quantity is varied in order to collect data that could be graphed to determine the value mu sub k, the coefficient of kinetic friction between the block and the horizontal surface. And we only have a meter stick. Okay, perfect. So for parts A and B, we're going to kind of do these sort of in a group. We need to indicate what could be measured by the students to allow them to determine mu sub k using a linear graph, and then describe a method to reduce experimental uncertainty. And for part B, we'll have to indicate what quantities they should graph on the horizontal and vertical axes to create a linear graph that could be used to determine mu sub k, and then describe the relationship between mu sub k and the feature of the graph in that part. Perfect. Okay, so let's take a look at what is going on here. So we'll kind of draw this out. So we have our curved ramp, and then we have the horizontal surface that has friction. And I believe the way this is going to work is we're going to have a block sort of maybe starting here with an initial velocity of 0 at a certain height above the horizontal surface. That block will probably transition to the surface with some sort of speed and kinetic energy, and then eventually reach a certain distance. So we'll call this distance delta x. So this should be the horizontal displacement on the surface. On the surface with the friction. And then we have this starting height h naught. Perfect. Okay, so if we're kind of thinking a little ahead here, we're going to probably start out with some initial gravitational potential energy. So if we draw an energy bar chart here, we'll have some gravitational potential energy. That is going to be the system of the Earth and the block, which means our initial kinetic energy is actually going to be 0. And then later on, those are going to flip-flop. So we'll have 4 blocks of kinetic. We'll make the gravitational potential energy 0 at the bottom of the ramp. But then after that, the block will then stop moving, and so they'll actually both be 0. And that is because there will be some work, negative work due to friction. So setting this up, we could say something like the mass of the block times the gravitational field constant times the initial height is going to equal that kinetic energy in the middle, which would then be the negative work due to friction. And so if I set this up a little further, we can say mgh naught is equal to negative the friction force times the displacement times the cosine of the angle between them. If we draw a force diagram here, we'll have a gravitational force, a normal force, those should be balanced with each other. And then we'll have our friction force. And that friction force is actually 180 degrees from the displacement, which is where that theta comes in to be 180. Actually, given all that, we could then say the friction force is equal to the coefficient of kinetic friction times the normal force, which is equal to the coefficient of kinetic friction times mg. So by substituting that down here, we'll get the negative sign canceling out with the cosine of 180, and we'll get mg h naught is equal to u sub k mg for our friction times the horizontal displacement. Those will cancel, and we should have something like this. And h, the initial height, should equal coefficient of kinetic friction times the horizontal displacement. Perfect. Okay. So given all that for part A, we'll say maybe measure the initial height of the block on the ramp with a meter stick. Write that down. We'll call that h naught of the block on the ramp. With the meter stick. We can release the block. and then measure the horizontal displacement on the surface the block reaches. We'll call that delta x with the meter stick. And that'll give us a certain value of h naught and a certain value of delta x. So we'll probably want to repeat this multiple times to reduce experimental uncertainty, and we can probably do that and get different values of the initial height and horizontal displacement. So we'll say all that repeats this procedure multiple times. For different initial height values. And record their corresponding horizontal displacements. Perfect. All right, that should be good for part A. Move on to part B. For part B, we are asked to indicate what could be graphed and then describe the feature of the graph and relate that to the coefficient of kinetic friction. Okay, perfect. So looking at the sort of brainstorming session we did, we could actually say, given that h naught should equal e sub k times the horizontal displacement, we could graph the horizontal displacement on the x-axis and the initial height on the y-axis. And the slope of that line, slope of the best fit line for that data should be equal to our experimental value for the coefficient of kinetic friction. That should work. We could just say graph h naught on the y-axis and delta x on the x-axis. And the slope of the best fit line should equal e sub k. However, if we wanted to do this with how we sort of designed our experiment, technically our delta x is our independent variable. Technically our initial height is our independent variable, and the corresponding horizontal displacement is a dependent variable. So we could do something like this. It's the exact same equation, just written a little bit differently. In that case, we would want to graph the initial height on the x-axis and the depending horizontal displacements on the y-axis. And the slope of that line should be 1 over the coefficient of kinetic friction. So you could also graph h naught on the x-axis, then plot delta x on the y-axis. And in this case, find the slope of the best fit line. And our coefficient of kinetic friction is equal to the inverse of that slope value. Perfect. I don't think you need to have both of these down. I think either or should suffice for part B. So 2 ways to sort of use the data to create a linear graph to find the experimental value for the coefficient of kinetic friction. All right, on to part C and D. In a different experiment, student released a block from rest on a rough ramp. The block is released a distance d from the photo gate, and the ramp is inclined at an angle theta. The block slides down the ramp, passes through the photo gate at the bottom of the ramp, and the photo gate determines the speed of the block. Okay. An unknown coefficient of kinetic friction in the block and the ramp is mu sub k. Perfect. Okay, so we have our table. We have values for D and V, and the correct relationship between D and V. So V squared is equal to the quantity 2G times the sine of theta minus mu k cosine theta equals D, where theta equals 30 degrees. Perfect. Okay, and we want to determine mu sub k. So just looking at this equation, it seems like we have V squared is equal to 2G times the sine of theta minus mu k cosine theta times G. So based off of that, we are going to plot D on the horizontal axis. So that's going to be our X variable. If we make V squared our Y variable, then that means we could take this entire expression, the 2G sine theta minus mu k cosine theta, and that should equal the slope of a best fit line of data that is V squared versus D. So I think we're going to want to graph V squared, which will have units of meters squared per second squared, since it's going to be the velocity squared on the y-axis. And hopefully that'll give us some linear plot, and then we can then determine what the coefficient of kinetic friction is. So to do that, we're going to create a second data table. So we'll have D here in meters, and then V squared in meters per second squared. Awesome. So the D values stay the same. There's 0.20, 0.30, 0.40, 0.50, and then 0.60. And then we're going to square all of our velocities. So I'll do that on a calculator. First value is 0.08. 0.08. Second value is 0.14. The third value is 0.17. Fourth value, 0.24. And then the last one is 0.27. Perfect. Okay, so it seems like it goes from 0 to 0.30. So we'll scale that graph appropriately. I think we can go by 0.05. So we'll do 0.05, 0.10, 0.10, 0.15, 0.20, 0.25, 0.30. That should be a linear scale. So that should work. And now we just have to plot the corresponding data. So the first point is 0.2, 0.08. So that's going to be right around here. Make a point there. Next one is 0.3, 0.14, which is here. Next one is 0.4, 0.17, which is here. Next one is 0.5, 0.24, which is here. And then the last point is 0.6 and 0.27. So it looks like we use most of the grid. We have a linear scale. This looks pretty good. So now all we have to do is draw a best fit line. So I'll take a ruler, try and approximate this as best I can. I think that looks pretty good. And we'll go with that. Awesome. Perfect. I'll erase a little bit of the edge here. Okay, that looks pretty good. All right, part C done. Part D, using the best fit line that we drew, calculating experimental value for mu sub k. So if we remember this correctly, the slope of our best fit line should equal 2g times the sine of 30 degrees minus the coefficient times the cosine of 30 degrees. They did tell us theta was 30. And so let's gotta find the slope of the best fit line. So we're gonna pick 2 points here. We'll pick this point here. And I think this point here, that should do it. Pick those 2 points. So this is points 0.33, 0.15. And the other one is 0.2. 0.507. Perfect. And now we gotta find the slope. So that's gonna be 0.15 minus 0.07 divided by 0.33 minus 0.2, which gives us about 0.6. That's equal to 19.6 times the sine of 30 minus mu sub k times the cosine of 30, which I believe is 0.866. And then we just saw that for mu sub k. So that is 0.6 divided by 19.6 gives us 0.03. That's equal to 0.5 minus 0.866 mu sub k, and then we can solve that. I think we end up getting about 0.54, which hopefully is in the range. So mu sub k is equal to 0.54.